There is a place in our solar system where an ocean has existed for longer than life has walked the surface of the Earth. Not a small pond, not a shallow sea. An ocean so vast, so deep, so ancient, that it contains more liquid water than every ocean, every lake, every river, every raindrop on our entire planet combined. And it is sitting right now, at this very moment, beneath the frozen crust of a moon called Europa. That alone should be enough to make you stop whatever you are doing. But here is the part of this story that almost nobody talks about. Scientists do not just suspect this ocean exists. They have a model for it, a detailed, peer-reviewed, mathematically coherent model that describes a specific region of that ocean that could be the most important location in the known universe when it comes to the search for life. A place where conditions might be so perfectly aligned that biology, actual living things, could have taken hold billions of years ago and might still be there right now. And NASA has no mission plan to explore it. Not one probe, not one lander, not one dedicated instrument pointed directly at the thing that scientists believe could be the most promising target in the entire search for extraterrestrial life. If you have ever wondered how we decide what to go looking for out there, and more importantly, what we choose to ignore, then stick around. Because what is happening, or rather what is not happening, with Europa's ocean, is one of the most fascinating and frankly baffling stories in modern space exploration. And if this is the kind of thing that keeps you up at night the way it keeps me up at night, make sure you subscribe right now, because we go deep on this stuff every single time. Let's start from the beginning. Europa is one of the 4 large moons of Jupiter. These 4 moons, Io, Europa, Ganymede, and Callisto, are called the Galilean moons because they were first observed by Galileo Galilei in the year 1610. He was looking up at Jupiter through one of the earliest telescopes ever built, and he noticed 4 tiny points of light that moved relative to the background stars. Night after night, he tracked them, and what he realized was that these were not stars at all. They were objects orbiting Jupiter. This was a genuinely world-shaking discovery at the time, because one of the central arguments against the idea that the Earth moved around the Sun was that the Moon orbits the Earth, and if the Earth were moving through space, the Moon would get left behind. But here was proof that objects could orbit something other than Earth, and that those objects could keep up just fine. Galileo's moons helped break open the old view of the universe. But it would take nearly 4 centuries before we would begin to understand just how extraordinary one of those moons truly is. For most of the time since Galileo spotted them, Europe looked like a small, faint, almost featureless point of light. Even through powerful ground-based telescopes, you could not make out much detail. It was a speck, a marble orbiting a giant. When Pioneer 10 and Pioneer 11 flew past Jupiter in the early 1970s, they got a slightly better look, but still nothing that revealed what was really going on. The real revelation came in 1979, when the twin Voyager probes swept past the Jovian system and sent back the first close-up images of the Galilean moons in real detail. When scientists first saw Europa clearly, their reaction was something close to disbelief. The surface of Europa is almost perfectly smooth. For a moon, this is bizarre. Almost every solid body in the solar system, every moon, every asteroid, every rocky planet, is covered in craters. Craters are the record of billions of years of impacts. Space is full of rocks and ice and debris, and when those things hit a solid surface, they leave marks. The more craters you see, the older the surface. The Moon, for example, is absolutely covered in craters. Mars is covered in craters. Even Earth, despite erosion and tectonics constantly resurfacing the planet, still has plenty of impact craters scattered around. But Europa has almost none. The surface of Europa is smooth and crisscrossed with a network of long, reddish-brown cracks and ridges that look almost like stretch marks on skin, or the surface of a cracked, hard-boiled egg. And the leading explanation for why there are so few craters is straightforward, but staggering. The surface keeps being replaced. Something is resurfacing Europa from below, wiping out the evidence of old impacts, creating a fresh new ice shell over and over again. The surface of Europa, scientists estimate, is geologically young, maybe only 40 to 90 million years old. In solar system terms, that is practically brand new. And the reason for this constant renewal The thing doing the resurfacing from below is the ocean. Here is how it works. Europa sits very close to Jupiter, which is by far the most massive object in the solar system apart from the Sun. Jupiter's gravity is so powerful that it does not just pull Europa into orbit, it actually squeezes it. As Europa orbits Jupiter, and as the other Galilean moons exert their own gravitational tugs, Europa gets stretched and compressed in a process called tidal flexing. Imagine squeezing a rubber ball in your hands, over and over again. That friction generates heat. The same thing happens inside Europa, but on a planetary scale. The tidal flexing from Jupiter generates enough internal heat to melt ice. And not just a little ice. Enough ice to maintain a global ocean of liquid water beneath the moon's outer crust. An ocean that, depending on which model you look at, could be somewhere between 60 and 150 kilometers deep. For reference, the average depth of Earth's ocean is about 3.7 kilometers. We are talking about a body of water that could be 40 times deeper than our own ocean, wrapped all the way around the inside of this frozen moon. The water ocean on Europa contains more liquid water than all of the oceans on Earth put together, possibly several times more. When the Galileo spacecraft arrived at Jupiter in the mid-1990s, the same probe that watched the Shoemaker-Levy 9 comet crash into Jupiter, it made multiple flybys of Europa, and those flybys confirmed what scientists had been theorizing since the Voyager data came in. The magnetic field data from Galileo was the key piece of evidence. Europa has an induced magnetic field, meaning it generates a secondary magnetic field in response to Jupiter's enormous primary magnetic field. The only thing that can produce that kind of induced field, the way Europa does, is a global layer of electrically conductive material sitting just beneath the surface. Salt water is electrically conductive. A salty, global subsurface ocean fits the data perfectly. The case for an ocean beneath Europa went from compelling hypothesis to near certain scientific consensus. And as the implications of that began to sink in, the conversation inevitably turned to life. Because here is the thing about life on Earth. Life, as far as we have been able to determine, requires three basic things. It requires liquid water. It requires a source of chemical energy, and it requires a set of raw chemical ingredients, things like carbon, hydrogen, oxygen, nitrogen, and a few others. For a very long time, we assumed that life also required sunlight. The entire food chain on Earth, we thought, ultimately traced back to photosynthesis, to plants and algae and bacteria, capturing energy from the sun and converting it into something living things could use. Without sunlight, the logic went, you cannot have life. Then, in 1977, a team of scientists operating the deep-sea submersible Alvin descended into the Pacific Ocean near the Galapagos Islands and discovered something that completely shattered that assumption. They found hydrothermal vents. Cracks in the ocean floor where superheated, chemical-rich water blasted up from the geological activity below, and around these vents, in complete and total darkness, kilometers below the surface where no sunlight had ever reached, they found ecosystems, not just microbes, entire ecosystems. Tube worms, shrimp, crabs, clams, fish, whole communities of organisms, thriving, eating, reproducing, living, in the dark, fueled not by sunlight, but by the chemical energy of the vents themselves. This process is called chemosynthesis, and it means that life does not need the sun. Life just needs energy, water, and the right chemistry. And now we knew that deep ocean floors, kept warm by geological activity, could host exactly that combination. Take a moment to sit with the implication of that. Because if life can exist in the deep, dark, geologically active oceans of Earth, and if Europa has a deep, dark, geologically active ocean, then the question is no longer whether Europa could theoretically support life. The question becomes, why wouldn't it? This is where things get very interesting, and also very complicated. Scientists started building models of Europa's ocean, not just rough sketches of what it might look like, but serious, detailed computational models that tried to account for the physics of the tidal heating, the chemistry of the water, the structure of the ice shell, the dynamics of heat flow through the moon's interior. And as these models developed over the years and the decades, a picture began to emerge. Not a uniform picture, not a simple picture, a picture of an ocean that is layered, dynamic, and in some regions potentially far more hospitable to life than others. The top of the ocean, just beneath the ice shell, is cold, possibly close to freezing. The pressure is relatively low there. The chemistry is influenced by whatever material has been mixed in from the ice above, which gets bombarded by radiation from Jupiter's intense magnetic environment and undergoes all kinds of chemical reactions that produce oxidants, things like oxygen and hydrogen peroxide, and other reactive compounds. These oxidants could theoretically be carried down into the ocean and provide a source of chemical energy for life. The bottom of the ocean is a completely different story. If Europa's interior is geologically active enough to generate tidal heat, and the evidence strongly suggests that it is, then the seafloor of Europa's ocean is not a cold, dead, inert expanse of rock. It is a place where heat is escaping from the moon's rocky mantle below, and where heat escapes from a seafloor into a water column, the chemistry changes dramatically. Minerals dissolve, hot fluids jet up through cracks, temperature gradients form, chemical gradients form, and chemical gradients, the interface between one set of conditions and another, are exactly where the most interesting chemistry happens, exactly where, on Earth, we find those hydrothermal vent ecosystems. There are models now, published in peer-reviewed scientific journals, that describe what the seafloor of Europa's ocean might look like. Models that calculate the likely temperature of the water near the seafloor, the mineral content, the potential for vent activity, the possible distribution of energy sources that microorganisms could exploit. And the conclusion that keeps coming up in these models, the finding that keeps appearing no matter how the numbers are refined, is that the seafloor of Europa's ocean is not just theoretically habitable, it may be the most habitable environment in the solar system outside of Earth. More habitable than Mars, more habitable than Titan, more habitable than Enceladus, the other icy moon that has captured so much scientific attention, more habitable in specific regions by specific measures than anywhere else we have ever identified in space. And this is the part that gets complicated, because while we have the models, and while the models are detailed and compelling and have held up remarkably well under scientific scrutiny, we have no specific mission designed to test them at the seafloor. None. Now, before we go further, let's be fair about what we do have, because it is not nothing, and the work that is being done is genuinely exciting. NASA's Europa Clipper mission launched in October 2024. This is a spacecraft that will reach the Jupiter system in 2030 and conduct dozens of close flybys of Europa over several years. It carries a sophisticated suite of instruments, cameras, spectrometers, magnetometers, radar systems, and instruments to analyze particles and plasma in Europa's environment. The goal of Europa Clipper is to confirm the presence of the ocean, characterize the ice shell, understand the moon's geological activity, and assess the habitability of the environment in a broad, systematic way. This is enormously valuable. This is exactly the kind of science that needs to happen. Nobody is dismissing the Clipper mission. It is a landmark achievement, and it will tell us things about Europa that we cannot even fully anticipate yet. But here is what Europa Clipper will not do. It will not land. It will not drill through the ice. It will not sample the ocean. It will not descend to the seafloor. It will observe Europa from orbit and during flybys. It will look, in extraordinary detail, from the outside. And looking from the outside, even in extraordinary detail, has fundamental limits, when what you are trying to understand is what is happening at the bottom of an ocean, buried under potentially dozens of kilometers of ice. The radar instrument on Clipper, called Reason, will attempt to peer through the ice shell using radio waves. This could reveal a great deal about the structure of the ice, and might even detect liquid water pockets closer to the surface. The magnetometer will refine our understanding of the ocean's depth and conductivity. The mass spectrometer will analyze the thin atmosphere and any material that has been ejected from the surface, looking for biosignatures or chemical signatures of what is happening below. All of this is invaluable. But none of it reaches the seafloor. And the seafloor, according to the models, is where the most interesting things are happening. Let me walk you through one of those models in more detail, because the specifics matter here, and the specifics are genuinely extraordinary. A series of studies, building on work that has been accumulating since the 1990s and substantially refined in the 2010s and into the 2020s, have modeled the hydrothermal system at the base of Europa's ocean. The fundamental question these models are trying to answer is this: is there enough geological activity in Europa's rocky interior to drive hydrothermal circulation at the seafloor? And if so, what does that circulation look like? The tidal heating mechanism we talked about earlier, the squeezing of Europa by Jupiter's gravity, does not just heat the ice shell, it also heats the rocky mantle beneath the ocean. In fact, much of the modeling suggests that the heat is generated primarily in the silicate rock of the interior, not in the ice, which means the seafloor of Europa's ocean sits directly on top of a geologically warm, potentially active rocky layer. Water in contact with warm rock dissolves minerals. It changes chemistry. It creates the conditions for hydrothermal activity. Some models have gone further and calculated the specific temperature and chemistry that would be expected at these seafloor vents if they exist, and compared those conditions to the conditions at hydrothermal vents on Earth, where life thrives. The comparison is favorable. Not identical because Europa's chemistry and pressure environment are different from Earth's in important ways, but within the range of conditions that we know, from direct observation on our own planet, can support microbial life. One particularly striking piece of work involves the modeling of serpentinization on Europa's seafloor. Serpentinization is a chemical reaction that occurs when seawater comes into contact with certain types of rock, particularly rock rich in minerals called olivine and pyroxene. This reaction produces heat, and it produces hydrogen gas, lots of hydrogen gas. And hydrogen gas is an energy source. Organisms on Earth, specifically a group called methanogens, eat hydrogen and carbon dioxide and produce methane, generating energy in the process. This is one of the most ancient metabolic pathways known. It operates in complete darkness, in oxygen-free environments, in conditions that would kill most life on Earth. And it is fueled entirely by the chemical energy of serpentinization, the rocks of Europa's mantle, based on what we know about how moons like Europa form and about the composition of the raw material that went into building the Jovian system, are expected to contain exactly the kinds of minerals that undergo serpentinization. The models suggest that serpentinization could be occurring right now on the floor of Europa's ocean, producing hydrogen, providing energy, potentially fueling an ecosystem. And we have no mission designed to go there and check. Here is where I need to explain something about how space exploration actually works, because the frustration around this situation does not come from any single bad decision. It comes from the structure of the whole enterprise. Planning, building, launching, and operating a space mission takes time. An extraordinary amount of time. Europa Clipper was first seriously proposed in the early 2000s. It was formally approved and funded starting around 2015. It launched in 2024. It will arrive at Jupiter in 2030, and then it will spend several years conducting its science. So from first serious proposal to end of primary mission, we are talking about something in the range of 30 to 35 years, from conception to completion. This is not laziness or inefficiency, at least not entirely. It is the reality of the physics. Getting to Jupiter is hard. Getting a large, sophisticated spacecraft to Jupiter takes time and enormous amounts of energy and money. The engineering challenges alone are staggering. Now consider what it would take to actually go further, to not just orbit Europa and observe it from the outside, but to land on it, drill through its ice shell, and send an instrument down to the seafloor. This is not a simple next step. This is an engineering challenge that makes the Clipper mission look relatively straightforward. And Clipper is not straightforward. It is one of the most complex planetary science missions NASA has ever attempted. The ice shell of Europa is estimated to be somewhere between 10 and 30 kilometers thick. Nobody is completely sure of the thickness, which is part of why Clipper's ice-penetrating radar is so important. But even at the optimistic end, 10 kilometers of ice, drilling through it is a colossal engineering problem. Ice at those temperatures and depths is not soft. It is hard, cold, and under pressure. A drill or a probe that descends through 10 kilometers of ice would need to carry its own power source, manage enormous thermal challenges, maintain communications with a surface relay station, and survive an environment that is hostile in essentially every possible way. There have been design studies, real ones, done by serious engineers at serious institutions. One concept that has received significant attention is called Thor, the Thermal Hierarchical Ocean Reconnaissance Probe, which would use heat to melt its way through the ice, rather than drilling mechanically. Think of a hot probe slowly sinking through the ice shell like a warm needle through a block of frozen butter, leaving a refrozen channel behind it, communicating back to the surface through a wire it pays out as it descends. This concept works, in principle. There are ice-penetrating probes being tested in Antarctica and Greenland right now, studying subglacial lakes on Earth as analogs for the conditions they would encounter on Europa. The technology is developing. It is not fantasy, but it is also not funded. Not for Europa specifically, not with a timeline, not with a mission architecture that connects it to the broader exploration program in a concrete way. And the reason, the honest, unsexy, deeply frustrating reason, comes down largely to money and priorities. The Decadal Survey, which is the process by which the planetary science community comes together every 10 years to decide what missions should be prioritized, recommended Europa Clipper as a flagship mission years ago, and that recommendation was eventually funded and executed. The next Decadal Survey, published in 2022, recommended the Uranus Orbiter and Probe as the next flagship mission, with Enceladus exploration also identified as a high priority. A Europa lander or ocean probe did not make the very top of the list. Not because scientists do not care about the seafloor, not because the models are considered unimportant, but because the sequencing of exploration follows a logic. You characterize before you commit, you orbit before you land, you observe before you drill. Clipper is the characterization phase. A lander or ocean probe would be the next phase. And the Decadal Survey process simply has not gotten there yet in terms of formal prioritization. There is also the question of what Clipper finds. If the data from Europa Clipper returns, and it shows that the ice shell is thicker than the optimistic estimates, that the ocean is less active than hoped, that the chemistry is less favorable than the models predicted, then the argument for a massive investment in a seafloor probe gets weaker. Science works this way. You follow the evidence, and right now, the evidence from Clipper does not exist yet because the spacecraft will not even arrive until 2030. So in a very real sense, we are waiting. The models exist. The case is compelling. The scientific community is largely convinced that the seafloor of Europa's ocean is a priority target, but the formal exploration plan has not caught up with the science yet. This might sound reasonable, and in some ways it is, but let's think about what we are actually saying here. We have a place in the solar system where we believe, based on solid physics and chemistry, an analogy with life we have directly observed on Earth, that conditions exist that could support life. We have models that describe the most promising region of that place in specific detail. We have even identified the chemical processes that could be fueling potential biology there. And our plan is to orbit the place, take good photographs and measurements from the outside, and then wait for the next Decadal Survey to decide whether we should think about planning a mission to go look at the interesting part. It is a bit like finding a door that every indication suggests leads to the most important room in history, and deciding to photograph the door very carefully before considering whether to open it. Now, I want to be balanced here, because there are serious arguments on the other side and they deserve to be heard. The first argument is about contamination. This is not a trivial concern. If Europa's ocean potentially harbors life, then any probe we send there must be extraordinarily carefully sterilized to avoid introducing Earth life to that environment. This is called planetary protection. We have strict protocols about this for missions to places like Mars, and those protocols would be even more stringent for a place like Europa, where the potential for a liquid water environment makes the contamination risk much higher. A probe that melts through the ice and drops into the ocean would need to be verified as having essentially zero microbial life on it. This is technically very difficult and adds enormously to the cost and complexity of such a mission. The second argument is about uncertainty. We do not yet know exactly where the most promising sites on Europa's seafloor are. We do not know the thickness of the ice in specific locations. We do not know whether the vent activity, if it exists, is widespread or concentrated in specific areas. Sending a probe to the seafloor before Clipper has characterized the ice shell and mapped the potential landing sites would be, in a very real sense, shooting in the dark. The data from Clipper will help us figure out where to target a future lander and eventually an ocean probe. The third argument is about cost. Flagship planetary science missions cost billions of dollars. The James Webb Space Telescope cost nearly $10 billion. Europa Clipper has a price tag of roughly $5 billion. A mission that lands on Europa, drills through the ice, and sends a probe to the seafloor would cost more. Potentially much more. In a budget environment where science is always competing with other priorities, making the case for spending that much money on a single target is difficult, even if the scientific case is compelling. These are real arguments. They have real weight. And they explain, without requiring any malice or negligence on anyone's part, why we are in the situation we are in. But I want to push back on something, not on the logic of the sequencing, but on the urgency. The universe does not wait for us to be ready. Europa's ocean has been there for billions of years, and it will likely be there for billions more. So in one sense, there is no rush. The seafloor is not going anywhere. Whatever is down there, or whatever is not down there, will still be there when we eventually decide to go look. But consider this. The models that describe Europa's seafloor as a potentially habitable environment are built on physics and chemistry and analogy. They are good models, but they are models. They are not observations. The history of planetary science is littered with cases where our models and expectations were overthrown by actual data. Mars was supposed to be a living world. It was not. Venus was thought to possibly harbor life in its early history. The more we look, the more hostile it appears. Our models are good, but they are not perfect, and they cannot substitute for direct measurement. Every year that passes without a concrete mission plan for Europa's seafloor is a year in which the most powerful question in all of science, are we alone, remains unanswered, not because we do not know where to look, but because we have not yet decided to look there. Let me tell you something about the scale of what we might be missing. On Earth, every ecosystem, every biosphere, every living thing from a bacterium to a blue whale is descended from a single common ancestor. We know this because the genetic code is the same in everything. Life on Earth, for all its staggering diversity, is one experiment, one origin, one branch of possibility. We have no idea whether the particular way life arose on Earth is the only way it can arise, or whether it is just one of many, or whether it arose at all in a special way that required very specific conditions that are rare in the universe. Finding life on Europa, even microbial life, even just a biofilm of ancient bacteria on a hydrothermal vent at the bottom of that cold, dark ocean, would instantly and irrevocably change everything we think we know about the distribution of life in the universe. Because it would mean that life arose at least twice, independently, in our own solar system, in two very different environments, under very different conditions, and if it happened twice in one solar system, the statistical implications are staggering. Life would not be a cosmic accident. Life would be a cosmic inevitability, something that happens whenever conditions are right, something that is probably happening right now on planets around other stars, in oceans under ice shells, in chemistry we have not even thought of yet. That is not a small thing. That is perhaps the most important thing in the history of human knowledge. And we have a model for where to look. There is another dimension to this story that is worth exploring, and it connects the specific situation with Europa to a broader pattern in how we approach the unknown. Throughout history, there have been moments where science had a model, a compelling, evidence-based, theoretically coherent model for something extraordinary, and the decision of whether to go and test that model turned not just on scientific merit, but on a complex mix of resources, politics, priorities, and frankly, imagination. The willingness to take the model seriously enough to commit to exploring it. When oceanographers first developed models suggesting that there might be hydrothermal vents on the deep ocean floor, the idea was not immediately acted upon. It took years before the Alvin submersible was sent down to look, and when it found not just vents but entire ecosystems, it changed biology forever. The model was right. The ocean floor ecosystems were there, and we found them because someone decided to go look. The moons of Jupiter were just points of light for 350 years after Galileo first noticed them. Then we built better telescopes. Then we sent probes. Then we discovered oceans. Each step required deciding that the thing was worth looking at more closely. The pattern is consistent. We build the model. We argue about whether to go look. We eventually go look. We find something that shatters our expectations and changes how we understand the universe. And then we ask ourselves why we did not go look sooner. Europa is at stage 2 right now. We have the model. We are arguing about whether to go look. Now let us talk about something that is often left out of the public conversation about Europa, because it complicates the narrative in an interesting way. The seafloor of Europa's ocean is not the only potentially interesting part of the ocean. It is, arguably, the most promising part based on current models. But there are other regions that have their own fascinating properties and their own advocates within the scientific community. The ice-water interface, the boundary where the underside of the ice shell meets the top of the ocean, is a zone of intense chemical exchange. Radiation from Jupiter hits the surface ice of Europa and drives chemistry there, producing oxidants and other reactive compounds. If those oxidants can be transported down through the ice shell and into the ocean, they could provide energy for life, even without hydrothermal activity. The question of how efficiently this transport happens is one of the big open questions in Europa science. Chaos terrain on Europa's surface, those jumbled regions where the ice looks like it has been broken up and refrozen, may be places where the ice shell is thin and where the surface and ocean are in more direct communication. These regions are of enormous interest precisely because they might be windows into the ocean, places where material from the ocean has made its way to the surface, or vice versa. Europa Clipper will study the chaos terrain regions in detail. This is one of the highest priority targets for the mission. If the data shows that there is regular exchange between the ocean and the surface in these regions, it opens a tantalizing possibility that we might be able to sample ocean material without drilling through the ice at all, simply by landing in a chaos terrain region and scooping up surface material that originated in the ocean. This is the concept behind a Europa lander mission, which has been studied extensively by NASA, but not yet formally approved or funded. The Europa lander mission concept, as it has been designed, would target a site in a chaos terrain region. It would carry instruments to analyze the chemical composition of the surface, looking specifically for biosignatures, molecular signatures of life. It would scrape and drill into the surface to collect samples and analyze them in a miniaturized laboratory on the lander. If ocean material really does make it to the surface in chaos terrain regions, then a lander could potentially detect signs of life without ever reaching the ocean directly. This is a compelling argument for why the lander concept might be more scientifically efficient than a direct ocean probe, at least as a first step. You might be able to answer the most important question, is there life, by sampling the surface, if the surface contains material from the right place in the ocean. But here is the complication. The material in chaos terrain regions comes from the top of the ocean, not the bottom. If life on Europa is concentrated at hydrothermal vents on the seafloor, far from the ice-water interface, then chaos terrain sampling might not tell you that. You might sample ocean-derived material and find no signs of life, and conclude incorrectly that Europa is lifeless, when the actual biology is kilometers below, at the bottom of a 100-kilometer deep ocean that the surface material never came into contact with. This is why the distinction between different parts of the ocean matters. This is why the seafloor specifically is such an important target, and this is why the absence of a plan to explore it directly is such a significant gap in our exploration strategy. Let's think for a moment about what a serious mission to Europa's seafloor would actually require, not as an engineering exercise, but as a way of understanding the scale of the challenge and why it has not happened yet. First, you need to get to Europa. This means a spacecraft large enough to carry all the necessary equipment, powerful enough to operate in the intense radiation environment of Jupiter's magnetosphere, and capable of surviving the long journey. Clipper has demonstrated that we can build such spacecraft. This part is hard but solved. Second, you need to land on Europa's surface. Landing on an icy moon with essentially no atmosphere and uncertain surface terrain is a significant challenge. You cannot use parachutes or aerobraking the way you can at Mars. You need rockets to slow your descent and sensors to navigate around hazards. This has never been done at Europa, but it has been done elsewhere. The Huygens probe landed on Titan. The various Mars landers and rovers have demonstrated soft landing technology. A Europa landing is hard, but within the range of current or near-future engineering capability. Third, you need to penetrate the ice shell. This is where things get genuinely novel. As we discussed, the ice shell may be 10 to 30 kilometers thick. A thermal probe, a cryobot, that melts its way through the ice would move slowly. At a rate of a few meters per hour in favorable conditions, penetrating 10 kilometers of ice could take years. Power is a massive constraint. A probe operating for years under the ice, far from any sunlight, needs a nuclear power source. Radioisotope thermoelectric generators of the kind used on Cassini and Curiosity could potentially provide enough power, but designing a cryobot around such a power source while keeping the whole system small enough to land on Europa is an enormous engineering challenge. Keeping the probe in communication with the surface through kilometers of ice using a wire or acoustic signals or some other method is another challenge. Preventing contamination of the ocean with Earth microbes while the probe sits on the surface for potentially years before entry is yet another challenge. Fourth, once the probe reaches the ocean, it needs to navigate in complete darkness in an alien ocean, find a hydrothermal vent site which may or may not be where we expect it to be, collect and analyze samples, and transmit the results back through the ice to the surface and then out to Earth. Communications from Jupiter to Earth have a round-trip light travel time of up to 96 minutes at maximum distance. Autonomous operation is not just desirable, it is essential. Every single one of these challenges is real and significant. None of them are obviously impossible. None of them are beyond the reach of a well-funded, well-managed engineering program that takes decades to develop. But together they represent a complexity and cost that is genuinely staggering, and that explains why, despite the scientific imperative, the mission has not moved forward. There are groups of scientists and engineers who are working on pieces of this puzzle. The Artemis Project, testing cryobot technology in Antarctic subglacial lakes. The work at Lake Whillans in Antarctica, where a probe successfully accessed a liquid water lake trapped under ice sheets. The development of autonomous underwater vehicles capable of operating without human direction. The refinement of nuclear power sources suitable for deep space and long-duration surface operations. The pieces are being built, just not for a specific Europa mission, with a specific timeline and a specific budget. What would it take to change that? Historically, the big leaps in planetary exploration have happened when the scientific case aligned with political will and adequate funding. The Apollo program happened not just because scientists wanted to go to the moon, but because the political climate of the 1960s created a context in which going to the moon was seen as worth the enormous cost. The Mars exploration program has been sustained over decades partly on scientific merit, and partly because Mars has captured the public imagination in a way that generates political support. Europa has the scientific case. What it needs is the same level of public awareness and political engagement that has sustained other programs. And I would argue that the scientific case for Europa is, if anything, stronger than the case that drove the Apollo program. Apollo taught us an enormous amount about the moon and the early solar system. It was a triumph of human ingenuity and courage, but it did not answer any of the deep questions about our place in the universe. Europa might. There is one more piece of this story that I want to make sure we talk about, because it changes the time horizon of the question in a way that is important. NASA is not the only player in space exploration anymore. The European Space Agency launched its own Jupiter mission, JUICE, the Jupiter Icy Moons Explorer, in 2023. It will arrive in the Jupiter system in 2031 and will spend time studying Ganymede, Callisto, and Europa. JUICE will not focus on Europa as exclusively as Clipper does, and it also does not include a lander or ocean probe. But it adds to the characterization effort, and the international scientific collaboration around the Jovian system is deep and productive. China has announced ambitious plans for deep space exploration, including eventual crewed missions to the outer solar system. though the timeline for any such missions is very long and uncertain. Private space companies like SpaceX have dramatically reduced the cost of getting to orbit, and while no private mission to Europa is on the horizon, the general trend toward lower launch costs does make more ambitious outer solar system missions somewhat more feasible than they would have been even a decade ago. The most optimistic realistic timeline for a Europa surface mission, one that actually lands on the moon and begins the process of accessing the ocean, would probably be sometime in the 2040s. For a full ocean access mission, the kind that reaches the seafloor, you are probably talking about 2050 or beyond. These are long timescales, long enough that the students who are in middle school right now could be the scientists and engineers who design and operate those missions. Long enough that the discoveries from Clipper will be well integrated into the scientific understanding of Europa before the next mission is even launched. Long, but not impossibly long. Not so long that it should make us feel hopeless. The thing about the universe is that it does not care about our timelines. The ocean under Europa's ice has been sitting there for perhaps 4 billion years. The chemistry that might be fueling life at its seafloor has been running on geological timescales that dwarf anything in human history. Whether we go look in 2040 or 2060 or 2080 is, from the ocean's perspective, essentially the same moment. The universe will wait. The urgency is not really about the ocean. The urgency is about us, about what it means to be a species that is capable of asking the greatest question of all time, and to stand at the edge of being able to answer it, and to not answer it. Every generation that passes without resolving the question of whether life exists beyond Earth is a generation that lived with that uncertainty when it perhaps did not have to. We have the physics, we have the chemistry, we have the models. We have, right now, a spacecraft on its way to Jupiter to begin the next phase of characterization. The tools exist or can be built. The question is not whether the ocean is there. The question is not even really whether the conditions at the seafloor are right. The models say they are. The question is whether we will prioritize going to find out. And right now, the honest answer to that question is, we have not decided yet. That is the part of Europa's ocean that we have a model for, but no plan to explore. Not any specific geographic location, though the hydrothermal vent regions of the seafloor are the specific target the models identify. The part we have not planned to explore is the deep ocean itself, the 60 to 150 kilometers of water column sitting beneath the ice, warmed from below by geological activity, potentially teeming with chemistry and possibly with life, that no instrument we have ever built has ever come close to touching. The models say go there. The science says go there. The history of every time we have sent a probe somewhere and been surprised by what we found says go there, and yet there is no mission in the formal planning queue that will go there within any timeline that any scientist currently working in the field will live to see the results from. This is not a criticism of any individual or any agency or any program. It is a description of where we are. And sometimes the most important thing you can do is describe clearly where you are, so that you can understand what it would mean to get somewhere else. We are a species that looked up at the sky for tens of thousands of years and wondered what was out there. We invented telescopes and saw moons around Jupiter and had no idea what they were. We sent robots to